Welcome to our second last unit of Secondary 3, your junior math class. So pretty exciting, we're on the tail end here, right? Here's the thing though. Last year, a lot of your geometry stuff you learned during Corona, which if you're online was similar to this. But I know that a lot of things they just didn't teach as much topics just because, the whole situation was brand new. So we did slim down the curriculum a teeny bit last year. So if there's anything that's confusing in this, it might be that it was a prerequisite from last year and it just wasn't taught. So if there's anything that's confusing, please email me and let me know. So notice this is notes and homework packet all in one. So it's going to be the notes, and then if you look at the calendar, and this will be clear in Canvas as well, you'll see the specific pages that you need to do in here as the homework. And then you'll also see which days you need to do a quiz. So you don't need to do a quiz every day. And every Wednesday there will be a short assignment. It shouldn't take you more than 5 minutes. So just be aware of that as well. All right, so we're going to jump right into 10.1. We're going to do a trig review and try to cover as much of the prerequisites that are super important, but also remember, like I said earlier, if there's something that is just not clicking, please email me, let me know, and I can make a video on that specific topic. So last year you were supposed to learn a lot about triangles and the relationships between their sides and angles. So just to kind of reinforce that, let's say that this is a 20-degree angle, right? So we can make a triangle at any point we want of that angle, right? So we could make skinny, small triangles, we could make big triangles. So, that angle has a lot of possibilities, basically, all right? So there's a relationship between the sides and the angles, just depending on where we decide to draw that side. So we're going to continue this exploration a little bit more. So what I want you to do is I want you to pause this video and I want you to work on 1, 2, 3, 4, and 5 and then come back and watch as I talk about it. So try it first, experience it first, and then we'll formalize these concepts and just see, just reinforce that, okay? All right, so pause, do it, then come back. So I'm going to order the sides of the triangles from smallest to largest. So the smallest side that I see is this red side down at the bottom. We'll call it side BC. So notice, if you're talking about a side, you just write the labeled points together with a line over it. The next biggest side is going to be side AC, and then of course side AB. So smallest to largest, this is just visually looking at it. And then smallest to largest angles, angle A looks like the smallest, then angle B, then angle C. And we actually know that angle C, if you remember this little square, means that that's 90 degrees. Just to remind you of that. And if you're 90 degrees, you're pointing to the hypotenuse. And hypotenuse is always the longest side of a triangle. So 90 degrees, hypotenuse, there you go. The largest side is going to come from the largest angle. So like I was showing you earlier, right? So this angle, right, the smaller the angle, the smaller the sides. B's middle in that, right? And depending on how big you want your triangle to be is where you'll end that, of course, right? So if we wanted a little triangle, but use these angles, so this angle B, even if it's over here, isn't changing as long as we keep that 90 degrees. But we can obviously change the size of our triangle, okay? So the size of the angle will correlate to the size of the sides. So keep that in mind. But the largest side is across from the largest angle. Okay, so number 2. What relationship did you see between these two triangles? So they have the same angles. Hopefully you notice that. They have the same angles. And we know that they're all the same because this is 90 degrees, as we just talked about. This is 90 degrees, right? So a whole triangle adds up to 180, so we could really easily find A. But even though they have all the same angle measurements, as you can see, they do not have the same side measurements. So number 3, in triangle 2, what is the length of the red side? How do you know? There's lots of ways to go about this, right? You could use the Pythagorean theorem, a squared plus b squared equals c squared. Because it is a right triangle, we could use the Pythagorean theorem, which is a great way to find that out. So you do 10 squared plus b squared, because this side is unknown, equals 12.5 squared. So notice this is always the hypotenuse. Hypotenuse is always the longest side. So we could put that in and figure this out. But another way to do this is, notice BC, okay, BC is actually going to have the same relationship. So 3 to 4, it's going to have the same relationship. So if we can find the relationship of these, and if we don't want to do 3 to 4, we could do 3 to 5, and we could do the unknown sign to 12.5, right? But they will have the same relationship, and I'll prove that in a second. But BC is 7.5, either using the Pythagorean theorem or that the relationship. Let me show you real quick. So if we do 5 times 2.5, we're going to get 12. If we do 4 times 2.5, we'll get 10. So you can see it's growing by a factor of 2.5. And so I did 3 times 2.5, and I got 7.5. So Pythagorean theorem using this growth factor, okay? So lots of ways to look at that. So side BC is equal to 7.5 because of the Pythagorean theorem, or because it should be 2.5 times bigger than this corresponding side from triangle 1. Okay, so we're going to look at some more ratios of these triangles, since now that we know that they are similar and are going to have a lot of properties the same, we're going to investigate that a little bit more. So if you take triangle 1 and do the green side over the blue side, you got 4/5, which equals 0.8, and you got 10 over 12.5, which equals, surprisingly, not surprisingly, 0.8. And then this side, we had 3 over 5, the red to the blue. That gave you 0.6. And then 7.5 over 12.5 gives you 0.6. And then 4 over 3 gives you 1.333. And then 10 over 7.5 gives you 1.333. So what is this telling us? Why am I making you analyze this and look at this? Well, there is a thing called trig ratios, which you might have heard of before. So sine of angle, so if you look at green and blue, we'll talk about this. If we look at them in relationship to angle B, they obviously have the exact same ratio, right? So these are trig ratios. And because of like how angles form and grow, they always grow proportionately. So if I cut it off and make a really small triangle, X and Y will have the same proportion as big X and big Y, right? Always have the same proportion, just because of how that angle as one side grows, the other side grows at a constant rate. So this ratio is going to explain that rate. And we use sine. Notice the green of angle B was opposite, and blue ended up being the hypotenuse. So this ratio, if we look at this angle and find the opposite side and the hypotenuse side to that angle, then we call it sine. That's just the ratio, that opposite and hypotenuse ratio. Here we're looking at the adjacent, it's right next to angle B, adjacent and hypotenuse. We call that relationship or ratio cosine. So in all of these we're analyzing angle B, and the last one is called tangent of angle B, which is 53.13. So pull out your calculator real quick, and what I want you to do first off, let's find my calculator. What I want you to do first is just hit mode and make sure that your calculator's in degrees. We're going to be working in degrees for a long time, so hit that and then get out of there, and I want you to hit sine of 53.13.8, right, when we round that. Sine of, nope, I want to do cosine, right? Cosine of 53.13. We get 0.6. Tangent of 53.13, 1.3333, right? So this is not surprising because the calculator has stored in its memory this relationship for angle 53.13. So really cool stuff, these trig ratios. So what do you notice about the values in the table? Why do you think this happens? Well, obviously the ratios, let me spell it right though, the ratios are the same in both triangles because all the sides are scaled the same amount. So if we analyze this again, right, if I have an angle, here let's say this angle is 15 degrees. So as we move out, that width, as we move out here, that width will always have the same ratio as moving farther out, because it'll get bigger obviously, right? So the angle is always expanding as we move out, if we move out in a straight line, which will make it expand at the same ratio. So sine of 15 degrees would give us the same opposite, let's just call it O, opposite over hypotenuse relationship ratio as opposite over hypotenuse, meaning that whole thing. Okay? All right. So a little bit more on this. Let's see. So there's a video that I was going to show, but it's not linking. I forgot that I pulled this in as a PDF. So I'll post that video. If you would like to watch it, you can. All right. So if you already worked on this, great. If you have not worked on 1 through 7, then pause right here and try these. Really try them. Read through the situation, give it a try, and then watch the explanation. So I promise you, if you experience the math first, you'll understand it way more. And as I talk about it, I think it'll click a little bit better if you are already on the same page as me. So I highly, highly suggest you pause this and then jump in with me. So pause and then hit play as soon as you're done with 1 through 7. All right, so the picture that I drew was give ourselves 90 degrees here because we have this ramp, and we have 32 degrees here and 113 feet here. Now I'm going to put a star right here because this angle is so important, and then I'm going to put an X here because that's what we're trying to find. So this angle of 32 degrees is what we're basing this whole ramp off of, right? yeah, we have the 113 feet, but that 30 degrees has a huge impact on everything about the ramp, as we just noticed in our previous problem set. So it says, which of the trig ratios, sine, cosine, or tangent, would be best to use to solve for the height? Why? All right, so I put a star here because this is the angle. Now remember, opposite that angle will be the x side. Adjacent will be the one touching that star angle, right? It's touching it. It's also touching the hypotenuse, but the hypotenuse gets its own name because it is the longest side. So we have opposite, adjacent, hypotenuse. Now, if you remember, SOHCAHTOA. This is just a little phrase that we use to help us memorize it. SOHCAHTOA, SOHCAHTOA. That means sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. So if I want to figure out x, if I want to solve for x, I want the opposite, right? So I'm probably either going to use sine or tangent. I'm not going to use this guy, right? And I know nothing about the adjacent, but I do know about the hypotenuse, so I'm going to use sine. Why would this be best? Because of the relationship that sine describes and what it asks us to find, right? Because the question wants us to find the opposite side, so we need to find the opposite side. And we have a value for the hypotenuse. Write an equation using the trig function and then solve it to find the height of the ramp. So sine, cosine, and tangent will always take degrees. That's what they take, or radians, depending on how we're measuring it. But they will intake that angle measurement. So the input is always an angle measurement. And it'll always equal the ratio. Okay, so sine of 30 degrees equals x over 113. And it's not degrees, it's feet, so I don't know why I wrote a degree sign. Sorry about that. All right, so what we're going to do here is we're going to multiply both sides by 113, right? So in my calculator, I'm going to do 113 times sine of 32, 113 times sine of 32, and I get 59.9 if we round. 59.9. So the height, 59.9 feet. If you think about that, that's so close to 6 basketball hoops. Basketball hoops 10 feet, right? So stacking 6 basketball hoops on top of each other, I'm a little bit afraid of heights. But to launch myself in a car off that height, whew, that takes guts, right? So kind of interesting. The landing ramp was constructed on a barge on the water. So if you've ever seen a barge, they're big, but if you've ever had to slam on your brakes, sometimes it takes a while to stop. So kind of an interesting situation that they put him in right here, or he put his engineers in. He had a limited distance to stop. So they needed a height of 98 feet with an angle of 36 degrees. That's just the physics of the car landing, that's what they needed. Okay, so we're going to draw a picture of this. Here's him landing. It was 36 degrees. I'm going to put a star right here because that's the angle that we're focusing on. And he had to land, it had to be from the barge to the top had to be 98 feet. And we want to know how much of the barge that's taking up, right, so that he can still stop. Okay, all right. Which of the trig ratios are we going to use this time? So notice that I put a star here to help me remember my orientation. That's where I'm analyzing this triangle from. So opposite of that star right? Opposite of that star is right here. So we have opposite, and here's my 90-degree angle. Here's hypotenuse. Here's adjacent. So what piece do we have? We have opposite, we want adjacent. It looks like we're gonna try to find tangent, right? Because that's what we have. Why? Well, I just explained it. Okay, 6. Write an equation for the trig function and then solve it to find the horizontal length of the landing ramp. So we have tangent. It takes that angle measurement. It's going to be 98 over x, right? Opposite over adjacent. So now I'm going to solve for x. So first I'm going to get it out of the denominator. And now I'm going to divide by tan 36, tangent of 36 degrees. Divide both sides by that. Remember, this x is gone, I canceled it out. So we have x equals 98 divided by tangent of 36 degrees. I actually already put that in my calculator, but I kind of ran out of room, so I'm going to write it right here. 134.89 feet. The landing barge was only 200 feet long. How many feet does this give him to stop the car? So 200 minus 134.89 equals 65.11 feet. Sweet. Okay. All right, so what is all this crap about? What did we just learn? Well, let me remind you. Important ideas. Write this down, memorize this stuff. Okay. So ratios of sides in a right triangle are determined by the angles. Ratios of sides in a right triangle are determined by their angles. So, if we have a right triangle, and this is the angle that we're focused on, we're going to call it theta. Theta is kind of the typical variable for angle measurements. This will always be the hypotenuse, because it's the longest side. Hypotenuse. This side will be opposite, because as you can see, it's exactly opposite that angle. And then this side will be adjacent. So sine of theta, sine of an angle, will be opposite over hypotenuse. Cosine of an angle will be adjacent over hypotenuse. And tangent of theta will be opposite over adjacent. All right, so what I want you to do right now is look over that, and I'm going to give you a little bit of extra practice here. Okay. So keep that, if you notice let me show you real quick. I left the bottom of this page blank for you to practice some of these. So we're going to do this one real quick. If you want to hurry and copy that down. You can also see this if you'd rather just open this file up and try a few of these with me. These are like the examples, right? So tangent of x. So here's our triangle. So that means that this is opposite, right? Opposite of that angle. The hypotenuse is always the longest side. It's always opposite. It's always getting pointed to by that right angle. So this is the hypotenuse. And then, so this angle that we're focusing on is touching the hypotenuse and always touching the adjacent. Okay, so we have all those. Tangent, if you remember, SOHCAHTOA, T for tangent. Tangent of angle x will be the opposite over the adjacent, which simplifies down to 4/3. So that will always be, whatever measurement this is, that will always be the relationship, okay? Even if this triangle increases in size, right? still that relationship of opposite over adjacent will always be 4/3. All right, so there's that one. Go ahead and try this one right here. So just give it a try. Sine of C equals what? Okay, so we're focusing here. So this is, it's touching, whatever angle you're focusing on, it's always touching the hypotenuse, which is the longest side, and adjacent, it's always creating the opposite. So just to label those. So sine, so, ka, toa, sine is opposite over hypotenuse, so 24 over 25, which I don't think simplifies very nice. Okay, let's look at another example over here. Just a reminder, put these in your calculator. So let's do cosine of 33 degrees. So if you put that in your calculator, cosine of 33 degrees, we get 0.84, right? So 0.84 is that ratio simplified. Now notice it's not in a fraction. I didn't change it to a fraction or see if it could. They won't always be in fractions, because like 24 over 25, if you remember when we did that one, right, we could put that in our calculator if we wanted to and find out what those degrees are, but the calculator is going to give you a decimal answer just because that's how it's programmed. Okay. All right, so let's take a look at 15. So here's our angle that we're looking at. It's 56 degrees. And look at the relationship. X is an opposite, adjacent, or hypotenuse. Opposite. 16, hypotenuse. So remember, so, ka, toa. We're working with sine here, right? So sine of 56 degrees will be opposite over hypotenuse. So I'm going to multiply both sides by 16, put that in my calculator, I'll get the answer. So 16 times sine of 56, I get 13.26. So that side, if we were to pull out a measuring stick, 13 point whatever I said, something, 26 or something. All right, so that is it for today. Hopefully you tried a few of those there. Take a look at the homework, and then I should post the key fairly soon, so watch for that as well. All right, good luck on your homework, and have a great one.